Hello everyone, my name is Grayson Duggar, and this is Physics 2212 Lab 1, Charged Tapes. The purpose of this lab is to determine the excess charge on tape and how it interacts with other objects, as well as using a computational model to simulate the interaction between the charged tapes. In this lab, we used the principles of Newton's second law of motion and Coulomb's law. The main result of this lab is that the charged tapes were both electron deficient, meaning that they were positively charged and they repelled one another. The magnitude of both electrical and gravitational force was 2.492 E-3 newtons. The charge on each tape was 8.945 E-9 coulombs, and the amount of electrons lost for each tape was 5.591 E10 electrons. Newton's second law of motion is a formula used to relate the mass and acceleration of an object to the force being applied on it, or F equals ma. Coulomb's law is a force used to show electrical force of one charged object upon another, and it is force equals K, which is a constant, times the charge of one, times the charge of another object, times the position vector. In our calculations, charges on each tape are modeled as a single point charge located in the center of the tape. This is done to simplify the process of finding forces between the tapes. We also make the assumptions that air resistance on a moving object is ignored. This allows for simpler calculations with regards to finding gravitational force. Also, we assume that each U-tape made had about the same amount of charge evenly distributed among the length of the tape. This enables us to find the charge of both tapes by finding the charge of just one. In our experiment, the system is the two pieces of tape, and the surroundings is everything else in the universe. The floating tape dimensions are 0.254 meters by 0.0254 meters, and its mass is 0.000254 kilograms. The distance of the floating tape away from the other piece of tape is 0.017 meters. Gravitational force is 0.00249 newtons downwards, because the direction of gravitational force points down. The electrical force is the opposite of this, 0.00249 newtons upwards. This is because the acceleration of the tape is zero, so the overall net force of the tape is zero. And since the two forces acting on the tape are gravitational and electrical, electrical has to be the opposite direction of gravitational. In my code, I created formulas using the mass of the tape, the separation between the two tapes, and known physics constants to calculate the magnitude of gravitational force and electrical force, as well as the charge and number of deficient electrons for each tape. The main difference between code and experiment are that in the experiment, both pieces likely don't have the same charge or evenly distributed charge, and the charge is not just located at a single point. Some possible sources of error for the experiment would be measuring the distance between the floating tape or the tape dimensions and treating the tape as a point charge, since the tape charge is likely not evenly distributed, so our modeled calculations do not accurately represent the experiment. Also, the amount of charge on each tape is likely not the same. As for our what if and why questions, what if the electrons have positive charge and protons had negative charge? What would change about the observations made with our tapes and other charged objects? And there would actually be no change in observation if charges of protons and electrons were swapped. Both tapes would have a flipped charge, but this also means they would have the same charge as one another, so the tapes would still repel one another. And what does this mean? Why is it important to handle the charged tapes as little as possible? What happens with the charged tapes when they come into contact with your hands or other objects? When they come into contact with other things, the more we handle the tapes, the higher the likelihood that excess charge from the tapes gets transferred to other objects, and this will decrease the charge on the tapes. In conclusion, we used this lab to model the effects of electrical force on objects in real life and created a computational model to help further visualize this phenomena.